Hello, and this week's video is going to be about basic transformations, so a reflection, a rotation, and a dilation, and I will go through them and show you some rules for them, the notation, and how to perform such transformations. This is geometric-wise, not functions-wise, but you can apply it to functions, I guess, as well. So, let's start off with reflections. So when you think about a reflection, what do you think of? Well, say you have a shape, and then you have a mirror, and then you mirror that shape into the mirror, and it stays the exact same. The area is the same. I know it doesn't look like on the drawing. The area is the same. The surface area is the same. You don't change anything about its shape, except you just mirror it. And now a circle isn't that great because all of its sides look the same. It doesn't have any sides, arguably. But for example, if you have a triangle that looks like this and you mirror it, it's gonna look something like this, right? It's not a copy and paste. It would not look something like this. It switches. So let's observe what happens. Anytime we have a shape and a mirror, we move each point so it has the same distance from the mirror. And then, for example, here, we can connect said points. So if you look at this, what do you think we're doing? Well, we have our mirror line over here. And anytime we want to mirror a point, say this point right here, we have to move it to a line that's perpendicular to the mirror line. And we keep the same distance. So this is D and this is also D. So our rules for mirroring something is that the point goes along a perpendicular line to the mirror, and that the distance between the mirror and a point is maintained from both sides. So how about we do an example to show what I'm really talking about? Alright, so this is our first task, where we want to reflect the triangle of given coordinates in the line y equals negative x. So first, how about we plot the points 2, 0, 2, 3, and 2, 2. This is our triangle over here. And we want to reflect it into the line y equals negative x. So unlike here, where our mirror was vertical, and thus the direction we move in had to be horizontal because that's the perpendicular, in this case, we're given a slight harder mirror line. So how about we quickly draw this y equals negative x? It doesn't have to be perfect, we just have to kind of be able to tell. So now, remember what I said. I said that we have to, or remember what you observed, because this is derived from common logic. We said that whenever we translate or move a point, reflect it, we're doing so in a direction that's perpendicular to the mirror line. So if our mirror line is y equals negative x, you must think, what is the slope of the line perpendicular to it? And that's just y equals x, right? That's the negative reciprocal. So now we can translate each point by moving it along y equals x. And remember how we said that the distance stays the same? So here we have this distance, square root of 2, and so do we here. So then this point gets moved here. On the other hand, if we do so with this point, it also has to move in this direction, but now it's 2 square root of 2's away. So this point is going to end up being here. And then lastly, we have this point, which also moves perpendicular-wise. And here we can count it like this, 1, 2.5, 1, 2.5. So over here, it's going to be moved here. So in the end, this is going to be our reflected triangle. And you might now see why it's useful to know that the line that we're reflecting is the line that is perpendicular, because this doesn't look that intuitive, or at least to me. So I would recommend keeping this in your head. Alright, so here we have rotations, and when we talk about the rotations, the notation is a rotation of theta about a point. And I'm going to show you an example to show what it is. So we want to rotate this by 90 degrees. So we want a rotation of 90 degrees, and just to make this simple, I'm going to say about the origin. So about 0, 0, right here. Alright, so to start off, let's move this point first. So we connect it to the origin via a line, and then we move it by 90 degrees. Now this is not accurate, and if you want to do this accurately, you should use a measuring tool to do so. So here, these should be kept the same lengths, and I'm just gonna, this is a rough estimate, but just so you know how to do it. So we moved this point by 90 degrees, right? Now let's move this one, and I'm gonna use a different color, just so you can tell better. So 90 degrees, I would say somewhere around like this here. And we have to make sure that the lines are around the same length. This is gonna be our other point. Now, lastly, let's move this point here, and then 90 degrees would most likely be something along these lines, and it has to stay the same length. And then we can connect said points to get something along the lines of this. So this is going to be our rotated shape. Now, it does not look very similar to this one, but that's just because A, I was not doing this with proper measuring devices, and B, this is just an estimation. And also, I find that rotations are rather unintuitive, so it might not always look as you expect, but this would be the rotation. And another way that you could do it is every point you have, you draw a circle that goes through the points, and this is how you know whether your distance or your length is equal. And I feel like this would have been better for me to do, is you draw a circle, and the radius of a circle is always the same, so this has to be your center, your origin point is the center, and you take a point, and then you measure however many degrees you have over here, which is 90 in our case, and then you move this point to reach next, if that makes sense. So let's quickly do a second example utilizing that circle method, and here we have a rotation of 90 degrees about the point A. So in this case, our center point is a point that we actually have on here. So we only have to move 2 points actually, which is pretty useful. So we draw a circle around the point A, and we really have to make sure that the circle is centered at A. So this is approximately centered at A, and what's really useful is I ended up drawing what looks to be like an isosceles triangle. So we can move each point on the same radius, and I don't have to draw, or in the same circumference, I don't have to draw multiple circles because that gets messy. So over here, we have our point, and then let's start with point B over here. And we're moving it by 90 degrees, and we're moving it counterclockwise. So 90 degrees from B is somewhere like this, I would say. So then our point is going to be moved here. And then for our second point, C. So 90 degrees for C, I would say, is somewhere like this. So our triangle, and I'm going to use a really bright color, would end up looking something like this yellow one here. And that's how you use the circle. If your points were not lying on the same circumference, then you will have to draw multiple circles. Now, last but not least, we're going to talk about dilations. And the way we refer to dilations, so the notation, is a dilation by a factor of k about a point. And what this means is that we have a point that's chosen, and say we have a shape. And each shape obviously also is made up of different points. And each point is connected by a certain distance to our point by which we dilate. And for example, here, this is the distance. This distance, let's call it d. If you're dilating by a factor of k, then the distance of this point right here after the dilation will be kd from the point by which you're dilating. So I'm going to show you an example to make this make sense. So this is the example. So it's actually 3. So we have a triangle which lies on these coordinates. And the first dilation that we're going to do is we're going to dilate it by 3 about the origin. So first, how about we plot this triangle? So we have 1, we have 1, 3, and we have 2, 1. So this is our triangle. And we want a dilation by 3 about the origin. So let's take this point to start off. Here, we're this distance away. And if we want to, because this is the origin, if we want to dilate it by 3, then instead of having this 1 unit, we need to have 3 of such units. So we have 1, we have 2, and we have a third one over here. So this is where our point is going to be. On the other hand, if we take, for example, this point, we have this distance right here. And we have to triple this distance. So we have 1, we have 2, and we have 3. Getting off the grid a bit. a big dilation. And then the last point that we have is over here. And it's this distance. So we have 1, 2, and 3. So it's going to be over here because we're multiplying this distance by 3. So in the end, our new triangle is gonna look like this. So this is our dilation. Alright, how about we do the second one? Alright, so this dilation, the second one, I changed the coordinates of the triangle because why not? And we have the point 1, 1, 1, 2, and 2, 1. So this is our triangle. And now we have a negative dilation. And what that means is basically that instead of going this way, we're going this way. We're going the opposite way. And it's about the origin. And it's by -2. So here we have this distance right here. But now we're going to have this distance twice, but in the negatives. Here we have this distance. So we're going to have it twice, but also in the negatives. So 1, and then 2, and the same on the other side. And we're going to end up with something looking like this. So this is going to be our new triangle over here. This is the dilation by -2 about the origin. Okay, so now let's do the last one. Alright, so this is our last example, and once again I switched the coordinate points because it will be way easier to see on this grid. So we have the point 3, 1, the point 5, 1, and the point 3, 6. So this is our original triangle. This is our pre-image. And we want to dilate it by the factor of 1/2 about, and I'm going to switch this real fast because I want to do this about the point 3, 1, and you will see why. I want to do it by the point 3, 1 because I want to do it by a point on the triangle itself. And this point right here, the 3, 1, it's going to be an invariant because it does not move. It's not affected by the transformation that we're going to do to it. So let's start. This right here, this point right here is 1, 2, 3, 4, 5. 5 units away. And our factor is now 1/2. So what could we possibly be doing? Oh, we could be shrinking the shape. So 5 divided by 2, or 5 times 1/2, well, that's 2.5. So now this point is going to be 2.5 units away, so around here. This point is 2 points away, so now it's only going to be 1 point away. And then we can connect all of these points to give us the dilated triangle. Alright, so I hope this was understandable, and I hope you're more familiar with the dilation, with a rotation, and with a reflection. And I hope you enjoyed this video. See you next time.